This week, we'll be dealing with acid-base reactions in lab, and in order to do the calculations, we need to know a little bit about stoichiometry. But first, we'll introduce you to the basic definitions of acids and bases. The Arrhenius definition is the first definition that you typically learn when you're learning about acids and bases. And in this case, an acid produces hydrogen ions, which are really just a proton, when dissolved in water. So hydrochloric acid is a great example of this. When you put this into water, the two ions dissociate from each other. Chlorine takes that electron and becomes chloride, and hydrogen ions or protons are also in water. Bases then are any species that produces hydroxide when dissolved in water. So sodium hydroxide is the quintessential base. When we put that into water, the sodium gives up its electron, hydroxide takes it for hydroxide ion, and then you also have sodium ions in solution. This week we'll be dealing with pH a bit as well, and I think people are generally familiar with the pH scale. High pH is a basic solution and low pH is acidic. When we calculate the pH, we're really looking at minus the log of the proton ion concentration, or the hydrogen ion concentration. If we're talking about basic, neutral, and acidic solutions on that pH scale, basic solutions have a pH greater than 7, but what that really means is that the hydrogen ion concentration is low. In fact, it's lower than the hydroxide ion concentration. So if this is a very small number and it's lower than hydroxide, then the minus the log is going to make it a large pH. Neutral solutions have a pH that's equal to 7, and in that case, that hydrogen ion concentration is equal to the hydroxide ion concentration. Acidic solutions have a pH that's less than 7, and that's where the hydrogen ion concentration is very large, or larger than the hydroxide ion concentration. So we'll be working with the pH scale this week. When we do an acid-base reaction, we typically have an acid and a base. In this case, we're going to show you hydrochloric acid with sodium hydroxide. When we put a hydrochloric acid into water, we know that that separates into the hydrogen ions and the chloride ions. We know that sodium hydroxide separates into sodium ions and hydroxide ions. The reaction that's actually occurring here is that these protons, or the hydrogen ions, are going to react with hydroxide to make water. And then what's left over is the sodium and the chloride ions, and this makes what we call a salt. So most acid-base reactions will result in water and a salt. We can write this balanced chemical equation in terms of the things that are actually present in solution. And so this is an example of a complete ionic equation, where we know that HCl does not exist as a molecule in solution. Rather, it's the hydrogen ions and the chloride ions. Same thing for sodium ions and hydroxide ions. And then we have liquid water, and then we still have sodium and chloride ions because of this aqueous here. That means it's dissolved in water. If we look at this complete ionic equation, you'll notice that chloride is the same on both sides. It hasn't changed. It hasn't actually reacted in this reaction, and so we can cancel that out. The same thing happens with sodium. It remains the same. It doesn't participate in the reaction, and so the reaction of interest is actually that the hydrogen ions react with hydroxide to make liquid water. Okay, so these things, that's the reaction of interest. The calculations that you might need to do for this are based on stoichiometry. And so this is the heart of any stoichiometry problem, is to figure out how many moles or how many molecules, right, of sodium hydroxide you would need to neutralize some amount of hydrochloric acid. So how many moles of sodium hydroxide are required to completely neutralize 0.37 moles of hydrochloric acid? We can start with the number that we're given, hydrochloric acid, but we recognize this as a stoichiometry problem because we're being asked, given some amount of acid, how much base am I going to need? And so given some amount of acid, how do I convert, or is there a conversion factor that will get me from acid to base? Now, the answer to that is that the balanced chemical equation will tell you how many of each you need in order to have a complete reaction. So I would need 1 hydrochloric acid for every 1 sodium hydroxide. That's either 1 molecule to 1 molecule, or 1 mole's worth of molecules to 1 mole's worth of molecules, because a mole is just a number of things. And if there's no number here in front of a chemical species, then it's just a 1 is that coefficient. So I can use these numbers from the balanced chemical equation, these coefficients, to write a conversion factor between hydrochloric acid and sodium hydroxide. In this case, I want hydrochloric acid in the denominator so that I can cancel moles of HCl, and my answer will be in moles of NaOH. So that's the heart of any stoichiometry problem. Now, a problem that you might actually need to do is something that looks like this. Given properties about the solutions, right? What is the concentration or what volume of sodium hydroxide would be required to neutralize 25 mils of 0.2 molar HCl? So in this case, I'm given everything I need to know about the hydrochloric acid solution, and I'm asked what volume of sodium hydroxide is going to be required to completely neutralize this. So this stoichiometry problem, we are completely using both reagents. We're not going to have any extra. There's no limiting reagent here. We're just, how much of this do I need to completely neutralize all of this so that I don't have any leftovers of either reactant? So what we do here is we recognize that in order to do stoichiometry, and I recognize this is stoichiometry because I'm asked going from species A to species B, okay? But I need to go to moles, okay? I have to go to moles so that I can use this 1-to-1 conversion factor. And so I can use my volume and my molarity of HCl to get to moles of HCl. Now I can use my conversion factor from my balanced chemical equation to get to moles of NaOH. And now that I have moles of NaOH, I need to find volume of NaOH. So I can use my molarity, which is moles per liter, in order to cancel moles and end up with liters. Okay, so I'm essentially dividing my moles by my molarity so that I can cancel moles and get to liters. So I would need 10 milliliters of this. To diagram, just to give you like an overview of stoichiometry problems, then you can think about this mole island diagram. If I have some amount of maybe a concentration of an acid and a volume of an acid, those two things I can put together to find moles of acid. And then once I have moles of my acid, I can get to moles of my base by using that mole to mole ratio from the balanced chemical equation. And then I can go back out using the volume to molarity, or use the molarity in moles to get to volume, or vice versa. But it's important to recognize that you have to go to moles to get to moles. In order to use that conversion factor from the balanced chemical equation, you have to go to moles first. So this mole to mole ratio, or the conversion from moles to moles, is really the heart of the stoichiometry problem. And in class, you may see how many particles or how many molecules of A get to grams of B, or how many, what molarity of A get to molarity of B, etc. You can come in to moles from any place, and you can go out from moles to any place, but you can't take a shortcut from grams of B to particles of A without going through this mole to mole ratio from the balanced chemical equation, okay? So we can practice this a little bit more and think about different types of acids. Polyprotic acids, for example, have multiple protons or multiple acidic hydrogens that can be removed to do a reaction. So poly meaning multiple, protic meaning protons. In this case, sulfuric acid has 2 of those acidic protons and a sulfate anion. Okay, so that's our acid. We can use sodium hydroxide again as our base. That's going to form water and a salt, sodium sulfate. Okay. We can write out the complete ionic reaction here. So we've got 2 protons and 1 sulfate. For every 2 sodiums and 2 hydroxides, we'll make 2 water molecules, and we will have left over 2 sodiums and 1 sulfate. So we can cancel out our spectator ions. And the important thing to recognize here is that every 1 molecule, so there's a coefficient of 1 out here for sulfuric acid, every 1 molecule of sulfuric acid has 2 protons, which is going to require 2 hydroxides, okay? And so our net equation, our net ionic equation is 2 protons for 2 hydroxides goes to 2 H2O. But if we're looking at the balanced chemical equation, it's going to be 1 sulfuric acid for every 2 sodium hydroxides. So we can do that first question over again. How many moles of sodium hydroxide are required to completely neutralize 0.37 moles of sulfuric acid? Again, we'll start with what we're given, 0.37 moles of sulfuric acid. We can now multiply by that conversion factor, which is 1 sulfuric acid for every 2 sodium hydroxides, okay? But now I want sulfuric acid in the denominator, and that's going to give me 0.74 moles of sodium hydroxide. We can do the more relevant question, the more relevant problem again. How many milliliters of 0.12 molar NaOH are required to completely neutralize 25 mils of 0.2 molar sulfuric acid? And again, we recognize this as a stoichiometry problem because we're given everything we need to know about species A, and we need to find something out about species B. So if we're trying to convert from one chemical to another, okay, then we will start with everything we know about sulfuric acid. I can use the concentration, moles per liter, times the volume in liters to give me moles. Now that I'm in moles, I'm into that center part of my mole island diagram so that I can use the conversion factor from the balanced chemical equation from moles to moles, so 2 sodium hydroxide for every 1 sulfuric acid. That's going to give me how much sulfuric acid, how many moles of sodium hydroxide I need. And then I can use that molarity again to get to volume of sodium hydroxide. So that gives me volume of sodium hydroxide required to neutralize all of my sulfuric acid. So we have a problem here that you can try. This is another polyprotic acid. This is phosphoric acid. It has 3 acidic protons for every 1 molecule. So what is the concentration of phosphoric acid if you've got 25 mils of phosphoric acid? If in order to completely neutralize it, you need 16.73 milliliters of 0.098 molar NaOH. So you can pause the video and try this on your own. Now in this case, you were given information about the base. So you're given the volume and the molarity of the base. So you can go to moles of base, and then you can use your mole to mole ratio from the balanced chemical equation to get to moles of acid. And then you can use the volume of the acid and the moles of the acid to find molarity. So in this problem, again, we're going to start with the base. Molarity times volume gives you moles of base. Moles of NaOH times the conversion factor from the balanced chemical equation. Now in this case, we want sodium hydroxide in the denominator rather than the numerator because we want to cancel out, right, sodium hydroxide and end up with moles of phosphoric acid. Once we have moles of phosphoric acid, we can divide by the volume of phosphoric acid to get the molarity of phosphoric acid.